Hello everyone, and welcome back to the Negative Light Studio, where we are on our journey to a Redstone computer. And today we're going to continue with one additional topic. Now you might be wondering, how are we going to get our data from, for instance, a RAM module to our CPU to maybe a monitor, a screen, or some kind of farm? Well, that's what I'm going to show you guys today, is transmission lines. So let's crack right into the video. Okay, so there are a couple things I'm going to talk about with transmission lines today. First is just what is a transmission line, how do they work, and then I'm also going to talk about some data that I've figured out how to calculate and what that means. So let's start with what is a transmission line. It's simply a way of getting some form of redstone signal from one place to another. And oftentimes, with especially a computer, you want to tile these so that they can transfer more information. For instance, you can design a system where 4 lines can transfer 15 different states of information. So 4 lines can hook up to 15 farms rather than 4 lines hooking up just 4. But this comes at the cost of, well, blocks. So first we're going to look at the green blocks. These are blocks that are necessary for the transfer line. You can't have the transfer line without those blocks. The yellow lines are what I label as unusable blocks. And how did I figure that out? Well, simple. Take a torch, and then if you cannot replace the block with a torch, it's unusable. And I might have missed a couple, but as you'll see in a moment, those values grow really fast. Because, like, I didn't put it on the top, for instance, just because I wanted you guys to see it. So you have unusable blocks, and you have the necessary blocks. Then a transfer line also has another attribute called delay. For some of them, it's controllable. For instance, with this simple single repeater line, which is basically it's going to go at the maximum distance that a redstone signal can. It can go between 1 tick and 3 ticks, but normally you're going to have it to 1 unless you need it for specific timings into some kind of machine. So that is this. So that's what a transfer line is. So let me go ahead and go through each one of these transfer lines, explain how they work to you, and then we're going to get right into the data of this situation. So first, you obviously have this simple repeater line. So when you flip a lever, it's going to transfer through the redstone line into the repeater, which is going to boost it back to 15, and then it's going to go back. And it can keep on going like that. Some of these do not use the full distance necessarily, and so I may adjust everything to match up properly, so that then everything is at its maximum possible distance. So we'll test that, and we can test that later on if you guys would like. If we can get to, let's say, 10 likes on the video, we'll actually go back, redo the calculations for it. Now, the next stage is the observer line. This is one that's really interesting to me because it's completely non-typical. So it uses powered rails, and then it goes the furthest distance, uses another observer, which then detects that and sends the pulse back down. And it uses a T flip-flop on the other end. So that makes this really unique and really powerful. It does have some extra unusable blocks in certain locations, but it's really similar actually to this. You need an observer every couple of spaces. This one does have one odd attribute, though, that is kind of interesting, is that it is very lag friendly. So one of the things with having like lots of redstone dust and repeaters and things like that is it can cause lag. So if you're in a laggy situation or you want something a little bit more compact, as you can see here, this number here is actually related somewhat to the compactness of it. It does kind of break for some of these somehow. I don't know how, because this is technically more compact than most of them. But yeah. Next we have the what's labeled as the InstaWire. So this one uses what's called a redstone block repeater, and actually these two can go out. Luckily that really is not going to damage my calculations terribly much because it's only 2 blocks. But basically when you flip this lever, it's going to power this piston, and then the piston is going to go into this line, and then that's going to go out all the way back for another 15 blocks, and you can connect it. But why is it called an insta-wire? Well, that's because pistons activate instantly. So you flip the lever, this line's going to activate, the piston's going to power instantly. And then the next piston's going to power instantly. And then the next piston's going to power instantly. Which means that you can basically go from where you're at to the edge of your render distance instantly. But obviously it does have some disadvantages of being a little bit bulkier. It does have fewer unusable blocks, so it is a little bit better. But you also have to use a full redstone block and a piston, which is much more expensive than a single repeater. So if you're trying to build it in survival, just keep that in mind. The next is probably some of the really compact, but really slow redstone lines. Now this is where the new sculk sensor is going to go in, and I'm going to be doing these calculations in a video in the future, hopefully with the sculk sensors, and updating this information as well. But how this works is pretty simple. You just have a repeater connected directly to a block, connected to a repeater connected to a block. There are other formats for this. For instance, there is one where you tile them, which will adjust it, but it increases the unused blocks. So I did not include it in this video today, just because I wanted to kind of showcase this and showcase the calculations a little bit more. Now, this has an 11 tick delay. It's really, really slow because for each one of these little modules, which is like a 2-block module, you have to have a repeater, and then a block, and a repeater and a block, and a repeater and a block. You could do like a repeater, a dust, and a block, and then, but again, as I said, that's going to increase your delay by 1, and then you could do right there, and then that's going to increase your unused blocks by 1, and then so on and so forth. It's going to keep on doing that. So you kind of have to, so for this video, I specifically used the single repeater. So it is really slow, but it is actually some of the most compact ones we have. And then finally you have this comparator one. Now this one is the only one that I'm showing today that transfers a total of 8 bits of information. All these other ones only handle 2. So you would have to basically take this and then double it and then double that again to even get to this amount of data that this one can transfer. That's why I have this full stretch here, and it's not the best, simply because that bit is not what I'm showing today. So this one also has an 11 tick delay, but it boasts the ability to kind of transfer a variety of information, including up to 8 bits of information. So that means that basically this right here can handle 15, not 15, holy cow, 31, is that right? 31 farms? No, that's not right. That is not right. It can handle a lot of farms and basically run your computer. Most redstone computers do not go past an 8-bit. Just because then things get really slow, really laggy, and really difficult. So let's get on to how I did the data and what I'm considering to balance each one of these and what I want to show you. So this first value is the one right here. This is the unusable blocks, meaning all of the yellow blocks. So even for these, including the block right above them, right? So this line of blocks per green block or necessary block. And you'll notice that actually you need about 2.3 of these blocks for each one of these. Now you're like, 2.3, hold up now. Hold up. But look at this, okay, you have this one right here would require 1, 2, and 3, right? And then this one would require 1, 2, and 3, but you'll notice this one is split in half, plus you have some extra blocks down here at the end, and you have these extra blocks right here. So it's around 2.3, but it could be up to 2.5 depending. And obviously the longer you make this and the more elaborate you make it, the more you can kind of adjust those numbers. The other thing that you also need to realize is that this bit right here is not necessarily unusable. So that's pretty good and pretty helpful if you're trying to do some things. I took advantage of this type of shape in my sculk sensor video, which you'll see in the iCard right up above, to actually make a 4-bit transmission intersection. So you can use this shape to your advantage and do that. The second value is what I call the bit rate distance density. So bit rate distance density. Now you're going to see this calculation on the screen right now. How I calculated this was I took the number of bits, so for instance for this one, 2. Then I divided that by the amount of blocks that it goes, so that would be the bit rate distance. So for these, it was about 24 for these. Then I divided that by the volume, and that gave me a density for that. So it's bit rate density times 1,000. I had to multiply these by 1,000 because the numbers were really, really, really tiny, is 0.262. So effectively, what that tells you is basically like the number of bits per block, per tick, per unit of volume. The other thing that I also had to do because of the InstaWire was I added 1 to the number of ticks for everything. So everything will remain the same, but it's just so that we don't break math. So the observer one had a bit distance rate density. Bit distance rate density. We're going to come up with a name for that, aren't we? Of 0.165. So for each one of these, for each one of bit of signal, it's going to take 0.165. It's going to be able to transfer 0.165 bits per block to the 4th tick. Yes, block to the 4th, because that is actually the units for that. And I can show you engineering analysis in the comments below if you guys would like. And right here is the repeater line. So it's unusable blocks to necessary block ratio is 2.25. So for each one of these blocks, you have 2 1/4 of a block that you must use. That's also why I use 2 lines, because that helps a little bit. Probably could, if you add more of these, that's probably going to go down towards closer to 2. Then you have the 0.552. So this is actually like one of the fastest ones. I believe it's not even beat by our comparator one because it's instant. It only has a 1 tick delay. Now, if you were to do the tiling, which kind of breaks with the comparator version, you can increase this. So there are versions here that probably have a higher value for that calculation. But yeah. So this one has a unused block to used block to necessary block value of 0.4. So, and that's just 0.478. So it's close to 0.5 because you only don't need this one. And it probably is only like that because you have 1, 2, 3, and then you'd have 1 there. So right here you have 1, 2, 3, then 2, and then 1, 1, 2, 3 with a 1 right there. Or 1, 2, 3 right there. 1, 1, 2, 3, 1, 1, 2, 3, 1, 1, 2, 3, 1. You kind of see. So a lot less. This one had the same exact value. They're pretty much the same exact lines. So if you really wanted to use this one and you want to transfer more bits, I suggest just using comparators because it's the same speed, it's got a pretty good accuracy, and fewer unusable blocks as far as a torch is concerned. Actually, I believe I have something wrong here. What happens when I take a torch and put... Nope, never mind. Even in subtract mode. See? Yep. Okay. Just making sure. It's always good as an engineer to double check your answers. So, and this one has a bit distance rate density of 0.426. So almost to the value of the InstaWires. Again, these are just a lot faster. So if you did need to just transfer a single bit, this is like the optimum way to go. But as you get further, these guys are going to probably lose out because, for instance, again, you need 8 of these lines to reach one of them. So you also have all of the extra hardware to transfer the 8 and do things like that. And for these, all you would need is 2 analog to digital converters for certain machines, and many machines can also be converted into an analog machine with the sacrifice of accuracy. So, mattering on your situation, you might want to do that. So, what can you learn from all of this information? Well, first off, you kind of now know various transfer lines, and hopefully I showed you something that you didn't know. Helps you maybe begin to think of how to compare things and how to do the math for that. I always like to do math and come up with equations to solve some answers or compare things, because sometimes that's necessary. Having a number to a value, even if it's something you're trying to achieve in life, really changes things and allows you to kind of understand it, compare and contrast. Some of these lines that I thought were better than the others were proven to be much worse, simply because there were some spots where you couldn't use blocks. And again, my values could be inaccurate because I'm not thinking of certain block positions, or maybe certain things should be considered unused for other reasons. But either way, like, this is pretty big and can change a lot. Is there anything that you can do to kind of like improve your Redstone computer with these? I don't know. Most of the time you're already using this design, which is pretty fast and is necessary for controlling timings, because with a computer, everything has to be timed very accurately. So something like this, though good, is also sometimes a problem. And I also wanted to check out what the skulk sensor does with this, because what we might find is that the skulk sensor actually is really good for transfer lines, which I have had some people mention that they're not that excellent to them, but we'll see. But without further ado, this is Negative Light signing out, and God bless y'all.